brains are impressive. With 14.6 watts of power, 1 millisecond time constant neurons, and a head space that is just enough to fit 2 pizza slices, and 100x fewer examples, they learn language. In contrast, a supercomputer on the AI cloud with a 10 gigahertz clock, a gigantic set of computer racks consuming 1 to 10 megawatt, with 100x more examples, learns language. But what I'm here to tell you today is that it's not just brains that are impressive, and brains are very impressive because they use analog, that is to say, noisy shades of gray, and probabilistic, that is to say, significantly random computation to do what they do, but that everything in nature, from atoms in physics to molecules in chemistry to cells in biology, are incredible because they use analog and probabilistic computers. So let me begin with the cell. With 1 picowatt of power, a cell does nonlinear random number calculus at 2-bit precise computation with asynchronous clocks that no supercomputer in 50 years has been able to replicate. In fact, if we could solve that problem, we would solve all of medicine. And it turns out that it's been estimated that to just simulate 20 minutes of the life cycle of a simple E. coli bacteria would take the most powerful supercomputer 12 years to do just 20 minutes in its full complexity. However, I've shown in my lab that if you map the chemical reaction basis functions, which are sort of the raw basis functions of how cells compute to analog electronic equivalent circuits, map their randomness to analog random electronic noise, that combination can improve the simulation 1 million-fold faster. And that means you can simulate something that would take 12 years in 6 minutes. And that means you can now rapidly search for cures and drug cocktails when the next pandemic hits, or even now, cures for cancer or any disease. Quantum computers are very well known in physics to take exponential superpositions of many, many, many possibilities all at once, keep them all alive, and then, like the focus of a lens that's taking all these waves that come together and interfere constructively at the focus, you get the answer with high probability and a high chance if it exists. And if it doesn't, you won't see it. It will all be blurred. And once again, this is very, very hard to simulate digitally. In fact, it's been proven to be impossible. But it turns out quantum mechanics is analog and probabilistic. The analog wave function, we have shown, can be emulated very faithfully, in fact, and very efficiently in analog chips. And the randomness and probabilistic measurement can also be emulated very efficiently, which means all sorts of quantum computing algorithms could be done very efficiently at the edge with very low levels of power, rather than hundreds of kilowatts of power and trillion-dollar budgets that only a few nation states can afford. Now, I'm teaching a course at Dartmouth that will launch this winter and spring called Analog and Probabilistic Computers from Quantum Atom to Living Body, which will go into the details of why and how this actually works in great depth that I won't have time to do here. But for now, I want to say, Alan Turing, the founder of computer science, actually understood this very deeply already. So in a way, we're going back to the future. He went from encryption that he was working on at GCHQ to designing programmable Turing machines, what we now really know off as digital computers today, universal Turing machines, to then suddenly realizing and working on analog reaction diffusion equations near his death. His work and the work of others, basically on biological development, showed that cells do amazing reaction diffusion equations. And in fact, with all the noise, all the error, all the asynchrony, all the low copy number molecules with wrong initial conditions and wrong errors, a baby is nearly perfectly formed after 40 cell divisions in the mother's womb. This is an amazing thing that happens when life gives birth to life. And it's due to some amazing nonlinear differential equations in the mother's womb that lead to pattern formation and the creation. So it's no surprise that the founder of quantum computing, Richard Feynman, said, the imagination of nature is much, much greater than the imagination of man. And before him, Euclid said, the laws of nature are the mathematical thoughts of God. And that's actually what we can do, because math is built into nature and we can reuse it. We don't have to reinvent it. And so I'm going to end by saying, may the force of analog and probabilistic computers always be in you, from every quantum atom to your entire living body, as it is in me right now. Thank you.